Have you ever really stopped to think about what happens in that tiny little moment after you hit send on an email or click on a link? Well, there's this hidden, massive global system that just springs into action, working at lightning speed to get your data exactly where it needs to go. Today, we're going to pull back the curtain on that very system, the network layer.
All right, so here's our roadmap. First, we're going to see how the network layer is basically the internet's own postal service. Then, we'll get into the weeds of routing versus forwarding. After that, we'll check out the two main ways our data connects, look at different kinds of digital delivery, and finally, we are going to crack the code of the good old IP address. Let's dive in.
So really, what happens when you hit send? Well, imagine you're mailing a physical letter. You don't personally walk it all the way to its destination, right? Of course not. You rely on this huge, complex, organized system to do it for you. And that is exactly what the network layer does for your data.
Yeah, at its very core, the network layer is the internet's global postal service. Its whole job is to move these little chunks of data, which we call packets, from a source computer to a destination computer. And it doesn't matter if they're in the same room or on opposite sides of the planet, connected by dozens of totally different networks. The network layer, it finds a way.
You know, every single time you're browsing the web, streaming a show, or sending a message, this absolutely brilliant, invisible system is just humming along tirelessly in the background. It's truly the unsung hero that makes our entire connected world even possible.
Now, to make this whole delivery system work, the network layer has to do two really critical jobs: routing and forwarding. The best way to think about it is like planning a huge cross-country road trip versus just making a single turn at an intersection. One is the master plan, and the other is the immediate, on-the-spot action.
So, routing, that's the big picture, strategic piece. A routing algorithm maps out the entire end-to-end path for your data before it even leaves. Forwarding, on the other hand, well, that's the local split-second decision. It's a single router looking at a packet that just came in and saying, okay, based on the master plan, you need to go out this door to get to your next stop.
And this visual just illustrates it perfectly. The routing algorithm is what comes up with that entire green path, all the way from the sender to the receiver. But forwarding? That's the individual decision happening inside router R5 and then again at R6, just to move the packet along that path, one little hop at a time. Now, just like our real-world postal service gives you different options, like certified mail or just a regular stamp, the network layer has two main ways of connecting and sending data. Let's call them registered mail versus standard post. So on one side, you have a connection-oriented service. The best analogy for this is making a phone call. A dedicated, reliable path gets set up between you and the other person before you even say hello. On the other side, you've got the connectionless service, which, by the way, is what the internet mostly uses. This treats every single packet like its own separate piece of mail. Each one gets a destination address and is just sent out into the system on its own. And they might even take totally different paths to get to the same final destination.
Okay, so if every packet is like its own piece of mail, who can we actually send this mail to? Well, it turns out the network layer supports a few different types of delivery, and each one is designed for a totally different purpose.
So first up is unicast. This is the one you use all day, every day without even thinking about it. It's a simple one-to-one delivery, one sender, one specific receiver. It's basically the digital version of sending a letter to a single mailing address. And yep, this is it in its simplest form. A private message, a request for a specific file, one source, one destination. Clean, direct, and to the point. Next, we've got multicast, which is a one-to-many delivery. Now, here's what's so incredibly smart about this. It's efficiency. Think of it like a magazine subscription. The publisher sends out one master version of the magazine, and the postal network is smart enough to make copies only for the neighborhoods where subscribers actually live. The sender doesn't have to waste time and energy sending a separate copy to every single person. And this is why it's so powerful. Whether you've got one person watching a live stream or 1,000, the source only sends out a single stream of data. The network itself handles all the replication. This is incredibly efficient, and it's the magic behind things like huge live video events and online gaming. Then there's Anycast. This one is a super clever one to the closest one of many delivery. You send a packet to what looks like a single address, but that address is actually being shared by a bunch of different servers all over the world. The network's job is to automatically figure out which of those servers is closest to you and send your packet there. This is the secret sauce for modern content delivery networks, or CDNs, that make websites load so fast for everybody.
As you can see right here, the sender isn't aiming for one particular green dot, it's just aiming for the green dot service in general. The network automatically finds the most efficient one to deliver it to, and that is precisely why a popular website can feel fast and local no matter where you are in the world. So let's do a super quick recap. Unicast is your direct one-to-one message. Broadcast, which you can see here, is more like a one-to-everyone shout on a local network. And multicast is that targeted one-to-a-select group message. 3 totally distinct ways to address our digital mail.
All right, so how does the network actually know where to send all these digital letters? Well, it all comes down to the address on the envelope, the IP address. So let's decode its anatomy.
You see, every IP address isn't just one long random number. It's actually made of 2 very distinct parts. The first part is the network ID. Think of that as the zip code or the neighborhood. The second part is the host ID. That's the specific house number on that street. Now, routers out on the internet mostly just care about that first part, the network ID, to get the packet to the right general area. Now, the original system for organizing these addresses was called classful addressing. And, well, it was pretty rigid. It created these different classes of networks. A Class A network was for just a handful of massive organizations, and it gave them a huge chunk of addresses. Class B was for medium-sized networks, and Class C was for millions of small networks. And Class D, as we saw before, that was just set aside specifically for those multicast groups.
So how does a router figure out the neighborhood part of an address? It uses something called a subnet mask. The easiest way to picture this is like a stencil. You lay this mask over the full IP address, and it cleverly covers up the house number part. What's left showing through the stencil is just the neighborhood part, the network ID. And that's how a router instantly knows if a packet is meant for its local network or if it needs to be sent out to the wider internet. So when you put it all together, the routing, the forwarding, the addressing, you start to realize the network layer is this invisible, genius-level postal service. It's the fundamental logic that stitches together billions of devices across thousands and thousands of networks into the one single internet that we all use every day.
But there's a problem. This system, the one we call IPv4, was designed decades ago, and it has a hard, unchangeable limit. It only has space for about 4.3 billion unique addresses.
You know, that number, 4.3 billion, it seemed impossibly huge at the time. But today, we have way more phones, laptops, servers, and smart devices than that. So here's the final, fascinating question. With so many more devices than addresses, why isn't the internet completely broken? Now that is a story for another time.